logical. And it can be named as such on YouTube and such. And I'm going to continue on. So, folks, we've taken main and we've added a parameter to it. And I've talked about how parameters that vary on a per person basis, per agent basis, if they vary on that basis, they're placed in the agent. If they don't vary across the population, or by extension, also, if they're used only at the global level, we'll put them in there. For example, if there's a contact rate, it doesn't vary by person. There's only one value for the entire model. We will put it in main as well, because it doesn't vary across people. It's an important principle. Okay. But now we're gonna get to work. Okay. We have miles to cover here. Okay. So we have this modest little model of heart disease. I want to now put into place an indication of a person's risk of dying from heart disease. Okay. And this is going to be something which will allow us to examine the effects of competing risks of developing heart disease and death. Okay. So we're going to go add in a representation of death within this model. And we're going to do it by going to the palette, going to this agent area at the palette, and I'm going to put in the final state here. It's in the palette. And it's a little dot inside a circle. Sometimes I think of it as kind of the Death Star. Okay. Okay. And now I'm going to draw. I'm going to allow for. Thank you, Jeff. That's awesome. I'm going to support death from either with a healthy heart or with heart disease. So we're going to draw here a transition, and it's going to come from healthy heart to heart disease. Now, I went awfully quick on that. So again, I'm getting it from a transition within the same palette. I'm dragging it, and sometimes it's handy to drag it up to the state whence it comes, from which it comes, so that it turns green. See that? It's turning green in mine there. I could see green is the color. And I do that because it's easier to hitch up. I don't have to worry about hitching up that side now. And then I can drag the other one down to whither it goes and make sure that's green. And there we go. The other alternative is, I can kind of drag in a disconnected way and sort of hitch up both sides, but it's somewhat more time consuming. So I tend to kind of drag it over its source state and then then hitch up the other end manually to the far side. You may notice that this is asymmetric, and you can actually go and click on this little indicator here of the rule type and to drag it in the middle. You can also engage in by appropriate clicking on this sort of link. You can actually bend it to your will if you're so inclined, and that can actually be very handy in certain circumstances. So you can double click on it to get a little handle, and in fact, you can do it with more than one handle. Oh no! Oh, okay. I can bend it, in various contorted ways. But right now I'm just gonna have it go straight because it's kind of useful. If you see that double, if you do the double click to bend it and you want to get rid of it, you can double click again. It'll sort of get rid of that. Okay. But if any of you want to kind of bend it around, you can. Okay. So we have two little arrows, one from heart disease, one from healthy heart. Okay. And these are both going to be rate transitions. They're both going to be stochastic, but we want to give them a name. In general, you want to give your transitions a name. TAs, take note. I don't know how many transition 35s I've seen in my student models. Transition 42. It's very unhelpful. So we want them to be intention revealing. You want a stakeholder to be able to look at them, see a name, and challenge it, critique it. We want to be vulnerable to our models to learn from others. Okay, so this transition will be called deaths with healthy heart. Okay. And I'm going to click show name. And when you do that, you'll notice it as this underline, and I'm going to drag it there next to it. So this is called deaths with healthy heart, or yeah, maybe I'll call it death with healthy heart. And it's triggered by a rate transition. And I'm going to make this rate with some pain in my voice, 0.0125. Why do I say some pain? Because properly, morally, I should really create a parameter that is shared between all people, and this should refer to that parameter. That parameter would live in Maine, and this would refer to it, and that would allow me to change it. In these teaching models, I often focus on teaching certain things, and that's a best practice that just cuts across models, and sometimes it's shortchanged by this. We'll be using it on an ongoing basis, but please know that it gives me the heebie-jeebies to see this, to like hard code it. I find it borderline reprehensible, and I feel a measure of guilt weighing upon my shoulders. Okay, enough of my soliloquy. So this is 0.0125 per year. Okay. Yeah, you know. Believe me. So I have a friend who's really good at car maintenance. And when I do maintenance on my car and jack it up and so on, he'll point out certain dangers, like take off the lug nut while the tire can't rotate, because if you do it otherwise. And I said, wow, you really know a lot. He said, yeah, like I've experienced every bad thing that can happen, like a car falling on him or whatever. And so it's made him just very conscious of the dangers, and so he takes action. And believe me, I've seen every bad thing that can happen here. And like I'm very conscious of the danger, and therefore I want to be heedful. And yet teaching requires me to sometimes concentrate on certain things, and I feel guilt. Does it have to be an exponential rate? No. If you want, you can draw it from your custom distribution. Make it a timeout and draw it from a distribution if you want it. It's just we're if you have to be very careful about where your assumptions about that distribution are coming from. So it certainly doesn't always come at an exponential rate, but often, as in survival analysis, it is parsimonious to, if you don't have data, better to make a simplifying assumption. And this is actually, I want to be conscious of the fact that this is a rate that imposes an exponential distribution. It's not an exponential rate. It's a rate that imposes an exponential distribution. What this means is for each successive day, there's a certain chance. It's like it's flipping a coin every day, right? This is a rate of 0.125 per year. It's exponential distribution in the residence time of this. So if you have a certain chance per unit time of leaving, that's fixed. Your time in this state will be distributed exponentially. This is why we use them in, competing risks analysis or survival analysis and accelerated failure time analysis as a generalization of it in biostatistics. That's a common representation because it's a simple assumption. And if you have more detailed data that you have appropriately analyzed, so that it can represent the time in that state in the appropriate conditional way, then you could draw it from a distribution. And you would do so with a timeout, and you would draw from, what do you want to draw it from? A Weibull distribution or something like that? Or you want to draw it from a beta distribution? You can do it. But I'm doing this to teach a very simple model, and I'm going to do it using a simple assumption there. Okay. And from heart disease, we're actually going to delineate deaths from heart disease with deaths from natural causes for people with heart disease. So this transition will actually be called deaths from heart disease. And we're going to have another parallel one that also will go to the death state that will be deaths of people with heart disease from natural causes. Okay. And we're going to delineate them because there may be certain types of interventions that are efficacious for one, but not for the other, for example. And I just want to illustrate this. Sometimes we we might want to delineate two particular generative pathways, particular causal pathways by which someone could die who has heart disease. So this will be deaths from heart disease. Excuse me, what am I doing? 0.35. So again, I feel the weight of guilt on my shoulders. And hopefully my students are feeling a proper degree of compunction in doing this and feeling a measure of queasiness, perhaps some of them even rightly feeling the heebie-jeebies. Okay, and then I'm going to sort of draw this here. Okay, I thought Jeff might show me a picture of him feeling the heebie-jeebies. Okay, here we go. So thank you, Jeff. This is awesome. Oh, we should have named that. We should have shown its name. Show names of things. It makes your model more transparent to stakeholders and to yourself. And I might add to my students for your supervisor. Okay. And this other one will be deaths. I'm tempted to say from natural causes. It's really deaths of people with heart disease from natural causes. We're not going to be able to lower that through certain heart disease therapies for people with heart disease. And so we break it out. And this is going to be a rate of 0.15. Notice that it's a bit higher than the 0.125 of people with a healthy heart, perhaps reflecting the fact that people with heart disease may tend to engage in other more sedentary lifestyle or lower a lower investment in other forms of healthy lifestyles. So the rate from natural causes while in a heart disease state may be higher, but the rates for dying of heart disease are pretty grievous. Okay. Okay. So we have transitions to this death state, but there's something we're missing, which is death is not occurring. Not occurring from this death state. And we have to make that occur. So go to the death state, and we're going to effectuate the death. We're going to make death occur in the model. And I want you to watch. I'm going to have to teach a few things here. So we're going to have to remove this person from the population. That's how death occurs. They're removed from the population. Where is the population in the model? Where does the population live in the model? Somehow I'm looking around person and I don't see it. Where can I find the population? Can anyone tell me? Where does the population live?
In Maine?
It's in Maine. So I have to tell the model, hey, remove me from Maine's population, from the population of Maine. How do I do that? Well, I have to say, hey, Maine's population, remove me. So this is how you do it in Java, okay? Main dot, not with an E, I might add. You're not talking about like remove me from Bangor or Portland or like South Brunswick or Monhegan Island. It's like Maine with a MAIN. Okay, enough said. Dot remove underbar population. Remove person. Oh, person. Okay, that's interesting. Wait, it used to be remove population, I thought, but okay.
Well, it's remove underbar the name
Name
of
of
the
the population.
population.
Yeah, but I thought in our model it was called population. Did we still call it person?
No, it's called person if you check in Maine.
Oh God. Oh, that's horrible. Okay. Okay. Well, okay. And now we have to say remove me. Who is me? It's this. This refers to me. And then I've got to say, do it. Do it. Like this is a command. It's not just calculating something, it's do it. Make it happen. And to do that, it's like an exclamation point. Do it. I do a semicolon like that. A semicolon. That's what it is. That's what it is. I can't believe I left it as person. I think it's because I said, oh, you don't have to change it here. I'll go change it elsewhere. Somehow anyway, okay, now that the guilt is even stronger. Okay. So basically what I'm saying is remove me from Maine's population, which is a thing called person, which is just like execrable. Yeah, Wade is doing the other way, which maybe is easier. There's a trade-off between them that is involves hybrid modeling and use of if you have a discrete event model and you're in a workflow. And Wade, do you want to comment on that?
Yeah, I think in a discrete event, if it's a hybrid model, you got to be more careful with deleting self. If it's
Right.
in a workflow, it might leave a null behind if you delete self.
Right. Whereas if you do this, I think it works. The remove population. But yeah.
Yeah, I'm not certain on that, but I'll defer to you.
I believe that's the case. That's my recollection, and we can discuss it later and do an analysis if you want. Okay. So if we run this model, now we see a population where, well, can anyone describe what's happening? Why is there a greater fraction of red circles over time that were there initially for the initial time? So I should probably be more careful about how I put that. For the initial time, like here, there's a rapid increase in the number of red, but then the number of red starts depleting faster. So what's going on there? Like, why is initially the fraction of red growing? Can anyone provide a mechanistic understanding of that?
Well, if there's more susceptible population in the beginning, there's more infected, and then
Excellent.
not no births, so basically we have less population for the same
That's
infection.
right. So over time, initially, the susceptible people with healthy heart are developing heart disease, so leads to more and more people with heart disease. But then what starts to counteract that? What other process? So that's one process, people are developing heart disease. What's another process that then starts to become pronounced in its interaction with that? People with heart disease start
Dying more often?
dying at higher rates than people without, right? So there's this kind of um, um, rapid acceleration number of people with heart disease, but that starts to be depleted faster than those without heart disease. And you see the results. Now, we're kind of visualizing it. Yeah, Jeff, be careful with renaming the population. Um, um, I, I, the population, I don't know, Wade can comment on these things, but in general, there are certain things in any logic I don't want to rename because it gets complicated. And I'm afraid, like a population, if I try to rename the population, I might stir up a hornet's nest. I don't know. Wade, do you want to comment on that? Or do you
It'll
think?
like if it'll throw an error because you've
Yeah,
called remove person,
right.
and the name of that will now change to remove
Okay.
population, for example. But
Okay.
once you correct that, there's no lasting negative effects as far as
Okay.
Isn't there a shortcut to like see what
Yes.
would change if you change
Yeah,
something?
there is. It's just there's one or two things which I've tried to change before, and it's caused like a hornet's nest of unhappiness and just cascading errors. And yes, there is, and we'll show it since Wade says it's safe. I'll trust that. But there are certain things I tend to try not to touch. Like I think maybe the name of the agent class or something like that, and like bad things happen if I touch it.
yes.
Okay. So I'm going to save this model. We're going to deploy it. This is going to be version 3 has death captured. And yeah. Does simulation no, the simulation continue the simulation continues right now indefinitely. It's a good question, but if you go to a given scenario, the scenario state how to run the model. And right now, if you go to a given scenario, the model time says never stop. So it'll keep going. But yes, I think after there's no more agents to do things and there's no events, etc., it will essentially say, okay, I'm done. If we want a different, yes, we would have to create different state charts. No, we don't have to, Sarah. We'll be seeing how we can make death rates, for example, change by smoking status or by age, by extension, etc. We'll see how to do that. Yeah, thanks. Okay, so I've just saved that version 3, and we're going to go on to version 4. Okay. Okay, now for this, what I'd like to do is move beyond our kind of high level glance at what's going on. I want to have numbers behind this, like how many people are there with heart disease? How many are there who have no heart disease? And I want to be able to plot that over time. Okay, so let's go to our model here, and we're going to create statistics in the model. So I think I'm going to stop